In 2017, a visitor from another star shattered every rule we thought we knew about space rocks. This needle-shaped object, racing at over 50 miles per second, was accelerating in ways that should have been impossible. No tail, no comet glow, just a dark shard tumbling through our solar system faster than anything we had ever seen from the inside. But that was just the beginning. You are about to witness how that first mysterious visitor led us to build the most powerful skywatching network ever created, and how in July 2025, we discovered something that makes that first object look ordinary. Like and subscribe to join us on this cosmic detective story. Prepare yourselves, we begin. October 19th, 2017 changed everything we thought we knew about visitors from space. Robert Wyrick was doing what astronomers do every clear night on Maui, scanning telescope images for moving dots among the stars. The Pan-STARRS telescope had captured something, and at first glance, it looked like any other space rock drifting through our cosmic neighborhood. Then, the measurements started coming in. This object was moving at 196,000 miles per hour. That is, 54 miles every single second. To put that in perspective, imagine a bullet traveling from New York to Los Angeles in just over 1 minute. That speed told astronomers one impossible thing. This visitor came from another star. Nothing from our solar system moves that fast. Our asteroids and comets cruise at a leisurely 12 miles per second on average. This newcomer was moving almost 5 times faster than anything bound to our sun. The speed meant it had been traveling through the vast emptiness between stars for millions, possibly hundreds of millions of years, before stumbling into our solar system. We gave it a Hawaiian name, fitting for the first messenger from the stars. The word means scout or messenger, arriving first from afar. But speed was just the beginning of its strangeness. As telescopes around the world tracked this visitor, they discovered something that made no sense. The object was tumbling end over end like a cosmic football, and its brightness changed dramatically every 7.5 hours. This told us the shape was unlike anything we had ever seen in space. Most asteroids are roughly round, like cosmic potatoes. Most comets are dirty snowballs, with irregular but compact shapes. This visitor was different, really different. The brightness changes suggested something 10 times longer than it was wide. Picture a skyscraper lying on its side, spinning through space. No known asteroid or comet in our solar system has such an extreme shape. The closest comparison would be a cosmic pencil or perhaps an alien spaceship, though that seemed too fantastic to consider seriously. Yet there it was, tumbling through our solar system like a shard of metal or rock carved by forces we could not begin to understand. As if the shape and speed were not strange enough, this visitor had one more surprise waiting for us. Something that would puzzle scientists for years and spark theories ranging from the scientifically plausible to the absolutely extraordinary. The mystery was just beginning to unfold, and what happened next would challenge everything we thought we knew about objects from other star systems. But compared to what astronomers would discover about its movement, the shape was just the warm-up act. The Panoramic Survey Telescope and Rapid Response System sits on the summit of Haleakala like a cosmic lighthouse, sweeping the Hawaiian skies for threats. Every night, this automated hunter captures images of space, looking for anything that moves against the background of distant stars. Most nights bring the usual suspects: main belt asteroids plodding along their predictable paths between Mars and Jupiter, an occasional comet wandering in from the outer solar system, sometimes a near-Earth asteroid that requires a closer look. But October 19th was different. The computer flagged something that made astronomers stop their coffee and stare at their screens. The Discovery images showed a faint dot moving across the starfield. At first, nothing seemed unusual about the movement itself. Space rocks move. That is what they do. But when astronomers calculated the trajectory, they realized they were looking at something that should not exist. This object was not orbiting our sun. It was passing through our solar system like a traveler on a highway, never to return. When you trace the path backward, it came from the direction of the star Vega in the constellation Lyra. But here is where it gets strange. The object took so long to reach us, about 300,000 years, that Vega was not even in that position when the journey began. This visitor had been wandering through interstellar space since before modern humans walked the Earth. It drifted through the cosmic void while our ancestors were learning to make tools and paint on cave walls. The Discovery team knew they had found something unprecedented. For decades, astronomers had predicted that interstellar objects should exist. Other star systems must occasionally fling asteroids and comets into the galaxy, just like our own system does. Gravitational encounters with giant planets can launch small bodies at escape velocity, sending them on million-year journeys between the stars. The math said these wanderers should be out there. Finding one was like looking for a specific grain of sand on all the beaches of Earth. But finding it was only the beginning. Once telescopes around the world started tracking this interstellar vagrant, the real mysteries began to emerge. The brightness measurements revealed that this was no ordinary space rock. The way light reflected off its surface told a story of a journey unlike anything in our experience. This object had been battered by cosmic radiation for hundreds of millions of years. High-energy particles from exploding stars and other violent cosmic events had slowly changed its surface color to a deep red, like rust on cosmic metal. The red color meant this traveler was old, really old. It had been wandering between stars since before our solar system settled into its current configuration. While Earth was still being bombarded by asteroids in the late heavy bombardment 4 billion years ago, this object may have already been drifting through space, carrying secrets from its long-lost home. Yet, even as astronomers celebrated finding the first confirmed interstellar visitor, they had no idea that the biggest mystery was still waiting to be discovered. Something about this object would soon defy every explanation they could imagine. Astronomers had never seen anything like what the brightness measurements were telling them about this cosmic visitor. As the object tumbled through space, telescopes tracked how its reflected light changed over time. Picture a cosmic lighthouse beam sweeping across Earth, but instead of a steady light, this beacon flickered dramatically every few hours. The brightness varied by more than 2.5 times as the object rotated. That much variation meant only one thing. This was no ordinary round space rock. Most asteroids are roughly spherical, like cosmic potatoes with bumps and craters. Even the most elongated asteroids in our solar system rarely stretch more than 3 times longer than they are wide. But this interstellar wanderer was different. The brightness changes suggested an object at least 10 times longer than its width. Imagine a skyscraper lying on its side, tumbling end over end through the vacuum of space. The shape was so extreme that some astronomers wondered if they were looking at a fragment. Perhaps this elongated shard was a piece of something much larger that had been shattered by a cosmic collision millions of years ago. Maybe 2 asteroids crashed together in another star system, and this needle-like fragment was launched into interstellar space by the violence of that ancient impact. But other scientists proposed an even stranger possibility. What if this object was not rock at all, but ice? In the cold depths of interstellar space, exotic forms of ice can exist that would be impossible near any star. Perhaps this visitor was made of hydrogen ice, formed in the heart of a molecular cloud between stars. The extreme cold and pressure in these cosmic nurseries can create materials unlike anything found in planetary systems. The hydrogen ice theory could explain the bizarre shape. As this interstellar iceberg approached our sun, the outer layers would sublimate away, carving the object into increasingly strange configurations. Like a cosmic sculpture being carved by starlight, the warming ice would reshape itself as it traveled deeper into our solar system. The process could transform a normal round object into the elongated needle shape that puzzled astronomers. Yet, even this exotic explanation faced problems. The object appeared too small and too dark to be made entirely of ice. Its surface reflected light like rock or metal, not the bright, shiny surface expected from an ice body. The red color suggested a surface that had been weathered by cosmic radiation for millions of years, slowly changing its chemistry in ways that ice could not survive. Some researchers proposed the most radical explanation of all. What if this was not a natural object? The unusual shape was unlike any asteroid or comet ever observed. The precise, elongated form looked almost engineered. Could this be debris from an alien civilization? Perhaps a piece of technology from another star system, designed for purposes we could not imagine? While most scientists remained skeptical of the alien hypothesis, they could not deny that this object challenged every assumption about natural space rocks. However, the shape was only the beginning of the mystery. The velocity measurements told a story that made astronomers question everything they thought they understood about objects in space. This interstellar visitor was not just moving fast, it was moving impossibly fast. At 196,000 miles per hour, it was traveling nearly 5 times faster than typical comets and asteroids in our solar system. To understand how extraordinary this speed was, imagine standing next to a highway where normal traffic moves at 60 miles per hour. Suddenly, a vehicle rockets past at 300 miles per hour. That is the cosmic equivalent of what astronomers were witnessing. The speed alone proved this object came from interstellar space. Nothing bound to our sun could achieve such velocity through natural gravitational interactions. Even our fastest spacecraft, when boosted by multiple planetary flybys, barely reach 40 miles per second. This cosmic wanderer was cruising at over 50 miles per second, carrying the kinetic energy of its million-year journey between the stars. But speed creates its own mysteries in space. When an object moves this fast relative to our solar system, it experiences effects that slower objects never encounter. The interstellar medium, the thin gas and dust that fills the space between stars, becomes like a cosmic headwind. Over millions of years, this resistance should slow down any object traveling through it. Yet this visitor maintained incredible velocity, suggesting it had not been wandering for as long as initially thought. The trajectory analysis revealed another puzzle. When astronomers traced the path backward to its origin, they found that this object had not been traveling in a straight line through space. Something had influenced its course during the long journey between stars. Perhaps it passed close to another star system, where gravitational forces bent its path. Or maybe it encountered one of the massive clouds of gas and dust that drift through our galaxy, each containing enough material to build thousands of new star systems. The speed also meant that observers had only a limited window to study this cosmic messenger. Unlike asteroids and comets that orbit our sun for months or years, this interstellar visitor was just passing through. It had already made its closest approach to the sun by the time astronomers discovered it. Now, it was racing away from us at tremendous velocity, growing fainter with each passing day. Telescopes around the world raced against time to gather as much data as possible before the object disappeared forever into the depths of space. Every night of observation was precious. Every measurement might reveal crucial clues about the nature of this visitor and the star system that had sent it on its cosmic journey. The pressure to understand this object quickly led to an international collaboration unlike anything seen before in astronomy. Observatories from Hawaii to Chile to South Africa pointed their instruments at this fleeting target. Radio telescopes listened for any signals that might indicate artificial origin. Infrared detectors searched for heat signatures that could reveal the object's composition. Yet, even as this unprecedented observational campaign gathered data, the object had one more surprise waiting for the scientific community. Something that would challenge the very laws of physics as applied to small bodies in space. In June 2018, Marco Micheli and his team at the European Space Agency announced a discovery that would send shockwaves through the astronomical community. This interstellar visitor was not following the path that gravity predicted. As telescopes tracked its movement away from the sun, the object was deviating from the trajectory calculated using only gravitational forces. It was accelerating, not dramatically, but measurably and consistently. The deviation was tiny, like a marble rolling down a perfectly smooth table, suddenly gaining an extra push from an invisible hand. The acceleration was about the same force you would feel if someone gently blew on your face. For a cosmic object traveling at tremendous speed, this represented a significant anomaly. In space, where there is no air resistance or friction, objects follow predictable paths determined by gravity alone. Planets, asteroids, and comets all obey these fundamental laws. This visitor was apparently writing its own rules. For astronomers, this represented a profound puzzle. The acceleration was in the right direction and had the right characteristics to be caused by outgassing. When comets approach the Sun, ice on their surface turns directly into gas in a process called sublimation. This escaping gas acts like a natural rocket engine, giving the comet a small but measurable push away from the Sun. The phenomenon is well understood and has been observed in thousands of comets, but this object showed no signs of the outgassing that creates comet acceleration. There was no visible coma, the bright fuzzy cloud of gas and dust that surrounds active comets. There was no tail streaming away from the object, as gas and dust particles are pushed by solar radiation. Telescopes saw only a dark, apparently solid object tumbling through space. Yet somehow, it was accelerating, as if it were a typical comet. The mystery deepened when astronomers calculated how much outgassing would be needed to produce the observed acceleration. For a normal comet, the amount of material being ejected would create easily visible signs of activity. The object would be surrounded by a bright coma spanning thousands of miles. It would sport a magnificent tail, visible to amateur astronomers with small telescopes. Instead, even the most sensitive instruments detected no trace of such activity. This led to increasingly exotic explanations. Perhaps the object was ejecting material that was too dark to see, like particles of pure carbon that would not reflect light. Maybe it was venting gas in narrow jets pointed directly away from Earth, making the outgassing invisible to our telescopes. Some scientists proposed that the acceleration came from the pressure of sunlight itself, acting on an extremely lightweight object. The light pressure theory required the visitor to have the density of foam or to be shaped like a solar sail. Sunlight carries momentum, and when it reflects off a surface, it can provide a tiny push. For most space objects, this radiation pressure is negligible compared to gravity. But for an object with the right combination of size, shape, and density, sunlight could provide measurable acceleration. This explanation led to the most controversial theory of all, about the nature of this cosmic wanderer, a proposal that would divide the scientific community and capture public imagination worldwide. Every spectacular comet that graces our night sky follows the same basic script written by physics and chemistry. As a comet approaches the Sun from the cold outer reaches of the solar system, solar radiation begins to warm its surface. Most comets are dirty snowballs, mixtures of ice and rock that have remained frozen for billions of years in the frigid depths beyond Neptune. When sunlight hits this ancient ice, something beautiful happens. The ice does not melt like it would on Earth. Instead, it sublimates, transforming directly from solid to gas without passing through a liquid phase. This escaping gas carries dust particles with it, creating the glowing coma that makes comets visible from Earth. The coma can grow larger than the planet Jupiter, spanning hundreds of thousands of miles of space. Solar wind, the stream of charged particles flowing from the Sun, pushes this gas and dust away from the comet, creating the magnificent tail that can stretch for millions of miles across the sky. The tail always points away from the Sun, like cosmic hair blown by stellar wind. This creates the beautiful sight of comets that seem to race across the sky, with flowing streamers trailing behind them. The process is so predictable that astronomers can forecast when a comet will develop its tail and how bright it will become as it approaches the Sun. But this interstellar visitor followed none of these rules. Despite showing the acceleration signature typical of a comet shedding material, it displayed no visible signs of activity. The most sensitive telescopes on Earth and in space detected no coma around the object. No tail streamed away from it. No dust particles reflected sunlight to create the characteristic glow of an active comet. This absence was not due to lack of trying. Astronomers used every technique available to search for signs of outgassing. They looked for the spectral signatures of common comet gases like water vapor, carbon monoxide, and carbon dioxide. They searched for reflected sunlight from dust particles. They monitored the object with infrared telescopes that could detect heat signatures from sublimating ice. Nothing. The Spitzer Space Telescope, one of the most sensitive infrared observatories ever built, stared at this cosmic wanderer for hours. If the object were shedding material like a normal comet, Spitzer would have detected the warm dust particles glowing in infrared light. Instead, the telescope saw only the object itself, dark and apparently inert against the background of space. This led to a crucial realization. If the object was accelerating without visible outgassing, then either it was shedding material in a way completely unlike any known comet, or the acceleration had a different cause entirely. Some scientists proposed that the object might be venting gas through cracks or vents that pointed away from Earth, making the outgassing invisible to our telescopes. Others suggested that the ejected material might be too dark to detect, like pure carbon particles that absorb rather than reflect light. But the most radical explanation suggested that this visitor was not a comet at all. Instead, it might be something far stranger, an object whose acceleration came from forces other than the rocket effect of sublimating ice. This theory would soon thrust a respected Harvard professor into the center of a scientific controversy that continues to this day. The astronomical community found itself facing a puzzle that seemed to violate everything they understood about objects in space. Multiple research teams around the world began working around the clock to find an explanation for this cosmic anomaly. The object was accelerating like a comet, but showing no signs of comet activity. This contradiction sent theorists scrambling through physics textbooks and computer models, searching for any natural phenomenon that could account for the observations. Alan Jackson and Stephen Desch at Arizona State University proposed that the visitor might be a fragment of nitrogen ice from a Pluto-like world in another star system. In this scenario, the object had been carved by sublimation during its approach to our Sun, explaining both its extreme elongated shape and its acceleration. As nitrogen ice vaporized from the surface, it would provide thrust while being nearly invisible to telescopes, since nitrogen gas does not glow brightly in space. The nitrogen ice theory was elegant and solved several problems at once. It explained the acceleration without requiring visible outgassing. It accounted for the strange shape as the result of uneven sublimation. It even provided a plausible origin story, since nitrogen ice is common on worlds like Pluto and similar objects that might exist around other stars. When gravitational encounters flung this fragment into interstellar space, it would have retained its nitrogen composition during the long journey between stars. Other researchers pursued different approaches. Some proposed that the object was made of hydrogen ice, a material that could form in the extremely cold conditions of interstellar molecular clouds. As this hydrogen ice approached the Sun, it would sublimate rapidly, providing acceleration while remaining essentially invisible to our instruments. The hydrogen gas would be too thin and dispersed to create a detectable coma or tail. A team led by Yun Zhang suggested that the visitor might be a fractal aggregate, a fluffy structure made of loosely bound dust and ice particles. Such an object could have an extremely low density, making it susceptible to radiation pressure from sunlight. The pressure of photons hitting the object could provide the observed acceleration without requiring any outgassing at all. Meanwhile, Avi Loeb at Harvard University was developing the most controversial explanation of all. Working with his postdoc Shmuel Bialy, Loeb calculated that the acceleration pattern was consistent with an artificial light sail, a thin reflective membrane designed to catch sunlight for propulsion. Such technology had been proposed for human space missions, and Loeb argued that an advanced alien civilization might use similar technology for interstellar travel. The light sail hypothesis suggested that this visitor might be a piece of alien technology, either a functioning probe sent to investigate our solar system or debris from some cosmic accident involving extraterrestrial engineering. While Loeb acknowledged that natural explanations were more likely, he argued that the scientific method required considering all possibilities that fit the data, no matter how extraordinary. The debate that followed would reveal deep divisions within the scientific community about how to handle anomalous observations and extraordinary claims. Yet, even as theorists battled over explanations, a new discovery would provide the most compelling solution to the mystery. In March 2023, Jennifer Bergner at UC Berkeley announced a breakthrough that would transform our understanding of this cosmic wanderer. Working with Darryl Seligman at Cornell University, Bergner had been studying what happens to ice when it travels through interstellar space for millions of years. The key insight came from understanding how cosmic radiation affects ordinary water ice during these incredibly long journeys. High-energy particles from exploding stars and other violent cosmic events constantly bombard objects drifting between star systems. When these cosmic rays hit water ice, they break apart the water molecules in a process similar to what happens in a particle accelerator on Earth. The energetic impacts split water molecules into hydrogen and oxygen, but in the cold vacuum of space, these fragments cannot escape immediately. Instead, the hydrogen becomes trapped within the remaining ice structure, like gas bubbles frozen inside a block of ice. Bergner realized that this process could continue for millions of years as an object travels through interstellar space. Over such vast timescales, cosmic radiation could convert up to 30% of the water ice into trapped hydrogen gas. The object would essentially become a hydrogen battery, storing energy from cosmic rays for millions of years until something triggered its release. That trigger would be the warmth of approaching a star. As the interstellar wanderer entered our solar system and began heating up, the ice structure would start to change. The warming would cause the ice to reorganize itself, collapsing the tiny pockets where hydrogen had been trapped. Like squeezing a sponge full of gas, this process would release the stored hydrogen into space. The escaping hydrogen would act as a natural rocket engine, providing the acceleration that had puzzled astronomers. But hydrogen is essentially invisible to most astronomical instruments. Unlike the dust and heavier gases that create visible comet tails, hydrogen produces almost no detectable signature when it escapes into space. The object would accelerate like a comet, while appearing completely inert to telescopes. This theory explained several key mysteries at once. It accounted for the acceleration without requiring visible outgassing. It provided a natural mechanism that could work on any water-rich object that had spent millions of years in interstellar space. It even explained why the acceleration was relatively gentle compared to typical comets, since hydrogen carries less momentum than the heavier molecules usually ejected by sublimating ice. The hydrogen outgassing theory also fit with what astronomers knew about the object's origin. If it had formed as a normal comet around another star and been ejected into interstellar space, cosmic radiation would have had plenty of time to create the hydrogen reservoirs needed to power the observed acceleration. The theory required no exotic materials or alien technology, just the predictable effects of cosmic radiation on ordinary ice over cosmic timescales. Computer models showed that the proposed mechanism could easily account for the magnitude and direction of the acceleration. The hydrogen release would naturally point away from the sun, creating thrust in exactly the direction observed by astronomers. However, the hydrogen theory still could not explain one crucial aspect of this cosmic mystery visitor. The discovery of the first interstellar visitor revealed a sobering truth that NASA scientists had suspected for decades. We were essentially blind to small objects approaching Earth from the depths of space. While existing surveys like Pan-STARRS excelled at finding large asteroids months or years before potential impact, They were designed to detect big threats from far away. But what about smaller objects, perhaps only a few hundred feet across, that could appear suddenly with just days or weeks of warning? The Chelyabinsk meteor of 2013 had already demonstrated this vulnerability. An object about 60 feet in diameter exploded over Russia with the force of 30 Hiroshima bombs, injuring over 1,000 people and damaging thousands of buildings. Despite all our sky surveys, this cosmic projectile arrived completely undetected because it approached from the direction of the sun, where telescopes cannot look. Larry Deno and his team at the University of Hawaii realized that defending Earth required a fundamentally different approach. Instead of looking for large objects far away, they needed to build a system that could scan the entire visible sky every single night, searching for anything that moved against the background of stars. This system would be optimized for finding smaller threats that might appear suddenly, giving humanity crucial days or weeks to respond. Thus was born the Asteroid Terrestrial Impact Last Alert System. The name itself captures the mission perfectly. This would be our last alert system, the final warning before impact for objects too small or too close for other surveys to detect. Atlas was designed to spot a 60-foot asteroid several days before impact and a 300-foot asteroid several weeks before impact. The engineering challenge was immense. To scan the entire sky every night required telescopes with enormous fields of view and extremely sensitive cameras. Each Atlas telescope would need to capture an area of sky 100 times larger than the full moon in a single exposure. The cameras would need to detect objects so faint they are invisible to the naked eye by a factor of 100,000. NASA funded the project with $5 million in 2013, recognizing that planetary defense required this new capability. The first two telescopes were built in Hawaii, positioned on Haleakala and Mauna Loa observatories, about 100 miles apart. The separation provided redundancy against weather and allowed for parallax measurements that could quickly determine the distance to newly discovered objects. By 2017, both Hawaiian telescopes were fully operational and scanning the northern sky every clear night. The automated system captured over 250 gigabytes of data nightly, with computers analyzing every image in real time to identify moving objects. The system could process the equivalent of the entire text of Wikipedia every single night, searching for the faint trails of cosmic wanderers. But the Hawaiian telescopes could only see the northern sky, leaving the southern hemisphere largely unmonitored. NASA recognized this limitation and funded 2 additional telescopes for the southern hemisphere. These new eyes would soon make a discovery that would dwarf even the mystery of the first interstellar visitor. By early 2022, humanity achieved something unprecedented in our history of watching the cosmos. 4 identical robotic telescopes, separated by thousands of miles across the globe, began working together as a single planetary defense system. The 2 original Atlas stations in Hawaii were joined by new installations in South Africa and Chile, creating the first survey capable of monitoring the entire dark sky every 24 hours. Each telescope in this global network represents a marvel of astronomical engineering. The optics capture light with mirrors only 20 inches across, smaller than many amateur telescopes. But what they lack in size, they make up for in field of view. Each telescope can image an area 7 4/10 degrees across, equivalent to 15 full moons side by side. This enormous field of view allows each station to photograph 1/4 of the entire sky in a single night. The cameras attached to these telescopes contain 110 million pixels, capturing detail across vast swaths of space with every exposure. To put this in perspective, if you printed out a single Atlas image at normal photograph resolution, it would cover an entire basketball court. Every night, the 4 telescopes together capture enough data to fill the memory of 50 high-end smartphones. The global positioning of these robotic sentinels creates overlapping coverage that ensures no blind spots remain. When it is daytime in Hawaii, the telescopes in South Africa and Chile continue the watch, When storms or volcanic eruptions affect one site, the others maintain surveillance. The 120-degree spacing between sites means that small asteroids, which might be visible for only a day or two, cannot slip through undetected. Each telescope follows the same precise routine every clear night. The system divides the visible sky into 1,500 separate patches, like a cosmic checkerboard. The telescope takes 4 30-second exposures of each patch, with the exposures separated by 10 minutes. This allows the computer systems to identify anything that has moved between the images, distinguishing between asteroids and cosmic rays, satellites and distant quasars. The data processing happens in real time at each site. Powerful computers analyze every image immediately after capture, identifying moving objects and calculating preliminary orbits. The system automatically compares each discovery against databases of known asteroids and comets, flagging only genuinely new objects for human attention. Within hours of discovery, confirmed new objects are reported to the Minor Planet Center, the international clearinghouse for asteroid and comet discoveries. This automated detection system has revolutionized our ability to find cosmic threats. Since becoming operational, Atlas has discovered over 700 near-Earth asteroids and 66 comets. The system has successfully detected 2 very small asteroids that actually impacted Earth, providing crucial validation of its ability to spot incoming threats. But Atlas capabilities extend far beyond planetary defense. As a byproduct of scanning the entire sky multiple times each night, the system has become one of the most productive surveys for finding supernovae, variable stars, and other cosmic phenomena. In July 2025, this global network would make a discovery that would reshape our understanding of visitors from other star systems. July 1st, 2025 started like any other night at the Atlas station, perched high in the Chilean Andes. The robotic telescope at El Source Observatory began its systematic sweep of the southern sky as the sun set behind the mountains. Automated systems powered up the sensitive camera and began the nightly ritual of capturing the cosmos, one patch at a time. Computer algorithms processed each image within minutes, searching for the telltale motion that betrays asteroids and comets moving against the stellar background. At first, the discovery appeared routine. The detection software flagged a faint object moving slowly across the starfield, typical of the distant asteroids that Atlas finds regularly. The preliminary calculations suggested an unremarkable space rock following a normal orbit around the Sun. The automated systems dutifully logged the discovery and prepared to move on to the next patch of sky. But as additional images accumulated throughout the night, something extraordinary began to emerge from the data. The object was not following the elliptical path typical of solar system objects. Instead, its trajectory showed the distinctive signature of a hyperbolic orbit, the same type of path followed by the mysterious first interstellar visitor years earlier. This new object was moving too fast to be bound by the sun's gravity. The discovery triggered immediate alerts to astronomers around the world. Within hours, telescopes in multiple countries swung toward the object's position, racing to gather observations before it could disappear into the depths of space. The Gemini North Telescope in Hawaii, the Canada-France-Hawaii Telescope on Mauna Kea, and the Lowell Discovery Telescope in Arizona all joined the observational campaign. Unlike the first interstellar visitor, this new object revealed its nature almost immediately. Through telescopes, astronomers could see a fuzzy, diffuse appearance surrounding a central bright core. The characteristic signature of ʻOumuamua was unmistakable. This was not a dark, inert rock like the first visitor. This was an active comet, complete with the glowing cloud of gas and dust that makes comets visible across the solar system. The presence of ʻOumuamua meant that this interstellar wanderer was shedding material as it approached the sun, just as normal comets do. Ice on its surface was sublimating into space, creating the beautiful display that has captivated humans throughout history. But this comet carried chemical signatures from another star system, offering an unprecedented opportunity to study the composition of materials formed around distant stars. David Jewett and Jane Liu, veteran comet hunters, confirmed the activity using the Nordic Optical Telescope. Their observations showed that the coma was clearly visible and growing as the object moved closer to the Sun. For the first time, astronomers were watching an active comet from another star system perform the same cosmic dance that our own comets have followed for billions of years. The discovery sent waves of excitement through the astronomical community. Unlike the enigmatic first visitor, this new object promised to reveal its secrets through well-understood processes. Spectroscopic analysis could determine the composition of its nucleus and coma. Imaging could track how its activity evolved as it approached the Sun. But the excitement came with urgency, as this cosmic messenger would not linger long in our neighborhood. The official announcement came on July 2nd, sending ripples of excitement through observatories and space agencies worldwide. The Minor Planet Center, the international authority for tracking asteroids and comets, issued the designation that would make history. Object C, 2025. N1 received the official interstellar designation, 3I, making it the third confirmed interstellar object ever discovered. The first had been the mysterious elongated visitor of 2017. The second was Comet Borisov in 2019, which behaved like a normal comet but arrived from interstellar space. This new discovery represented something unprecedented. For the first time, astronomers had detected an active interstellar comet while it was still approaching the Sun, not after it had already begun its departure from our solar system. This timing advantage meant that observers would have months to study the object as its activity increased, rather than the desperate race against time that characterized observations of the previous visitors. Pre-discovery observations quickly emerged from telescope archives around the world. The Vera Rubin Observatory had actually imaged the object during its science validation observations starting June 21st, though the images had not been processed until after the Atlas discovery. NASA's Transiting Exoplanets Survey satellite had captured the comet even earlier, with observations extending back to May 7th, when it was still over 6 times farther from the Sun than Earth. These archived observations revealed that the interstellar comet had been active for much longer than anyone expected. Even at enormous distances from the Sun, where water ice should remain frozen solid, the object was already showing signs of sublimation. This suggested that its activity was powered by more volatile materials than water, possibly carbon monoxide or carbon dioxide, that can sublimate at much lower temperatures. The trajectory analysis confirmed what astronomers had suspected from the first observations. When traced backward through time, the comet's path clearly originated from beyond our solar system. It had approached from the direction of the constellation Sagittarius, where the central bulge of our galaxy creates a dense concentration of stars. The object had been traveling for millions of years before encountering our Sun's gravitational influence. Unlike the first mysterious visitor, this new interstellar comet posed no puzzles about its acceleration. The growing coma and emerging tail explained its motion perfectly through well-understood physics. As ice sublimated from the nucleus, the escaping gas provided a natural rocket effect that gently altered the comet's trajectory. There was no need to invoke exotic materials or controversial theories. The discovery also vindicated the global Atlas network's design philosophy. By scanning the entire sky every night, the system had detected this visitor while it was still far enough from the Sun to allow extensive observations. Earlier detection systems, focused on finding large threats months in advance, would likely have missed this smaller object approaching from the southern sky. Within days of the announcement, the Hubble Space Telescope had acquired its first images of the interstellar visitor, revealing details about its coma structure and composition. These observations would unlock secrets that had been traveling between the stars for millions of years. The first detailed images from the Hubble Space Telescope revealed a sight that had never been captured before in human history. Here was an active comet from another star system, displaying the same beautiful phenomena that have inspired skywatchers for millennia. The coma stretched over 8,000 miles across, a glowing cloud of gas and dust that made the tiny nucleus visible across the vast distances of space. Spectral analysis revealed the familiar signatures of water vapor, carbon monoxide, and carbon dioxide, the same materials that power comets born in our own solar system. But this cosmic visitor carried subtle differences that revealed its alien origin. The dust particles in its coma were larger on average than those typically found in solar system comets. Measurements showed that small dust grains, about 1 micrometer in radius, were being ejected at speeds of 72 feet per second. Larger grains, 100 times bigger, moved much more slowly at about 6.5 feet per second. These dust properties told a story of formation in a different stellar environment. The comet had likely formed in the outer regions of another planetary system, where different temperatures and chemical conditions created ice mixtures, unlike those found in our solar system's comet reservoirs. The larger dust grains suggested that the parent star system may have had more heavy elements available during planet and comet formation. As July progressed into August, telescopes tracked the steady growth of the coma as the interstellar visitor continued its approach toward the Sun. The Canada-France-Hawaii telescope captured images showing the emergence of a faint tail, the classic elongated feature that points away from the Sun as solar wind pushes the comet's atmosphere into space. For the first time, astronomers were watching an interstellar comet develop its full regalia of activity. The tail itself carried important information about the comet's composition and the solar wind conditions it was encountering. Unlike the invisible hydrogen that might have powered the first mysterious visitor, this comet's tail contained easily detectable dust and gas that revealed their chemical makeup through spectroscopy. Each element and molecule left its unique fingerprint in the light reflected and emitted by the tail. Ground-based telescopes around the world joined the observation campaign, creating an unprecedented international effort to study this messenger from the stars. The Gran Telescopio Canarias, the largest optical telescope in the world, determined that the comet's nucleus was rotating once every 16.75 hours. This rotation rate was typical of small comets, suggesting that despite its interstellar journey, the object had retained the basic physical properties of its birth environment. The European Southern Observatory contributed observations that tracked how the comet's brightness varied as different parts of its nucleus rotated into sunlight. These brightness variations decreased over time, indicating that the nucleus was becoming more uniformly active as its approach to the Sun warmed previously frozen regions. Unlike the enigmatic first interstellar visitor, this new cosmic wanderer was behaving exactly as astronomers expected an active comet to behave. Every observation confirmed that it was following the same physical laws that govern comets throughout our solar system. Yet the very normalcy of its behavior carried profound implications for our understanding of planetary system formation across the galaxy. The scale difference between the two interstellar visitors reveals just how much we missed with the first mysterious wanderer. While astronomers never determined the exact size of the first elongated visitor, estimates suggested it measured somewhere between 300 and 3,000 feet in length. Picture a large skyscraper tumbling through space, perhaps the height of the Eiffel Tower, but stretched into a cosmic needle. That object was already at the limit of what telescopes could detect as it raced away from our solar system. This new interstellar comet dwarfs its predecessor by orders of magnitude. Early estimates suggest a nucleus several miles across, making it roughly 100 times more massive than the first visitor. To put this in perspective, imagine comparing a school bus to a small city. The difference in size translates directly into observational opportunity, giving astronomers vastly more material to study and analyze. The larger size explains why this comet can produce such a spectacular display of activity. With more surface area exposed to solar heating and vastly more ice available for sublimation, the comet can generate the bright coma and tail that make it visible to telescopes around the world. The first visitor, even if it contained ice, was simply too small to produce detectable outgassing under most circumstances. Size also determines how long an object remains observable. The first interstellar wanderer faded from view within months of discovery, becoming too faint for even the largest telescopes to track. This new comet, with its substantial nucleus and active coma, will remain visible to ground-based telescopes for many months, allowing for extensive study of its composition and behavior. The mass difference affects how the two objects respond to solar radiation pressure. The first visitor's small size made it susceptible to forces that barely influence larger objects. Sunlight pressure, magnetic fields, and even the solar wind could potentially alter its trajectory in measurable ways. This new comet, with its much greater mass, follows a more predictable path, determined primarily by gravitational forces. The substantial size of this interstellar comet also provides crucial information about the planetary system that ejected it into space. Large comets require significant reservoirs of ice and dust to form, suggesting they originate from systems with substantial debris disks during planet formation. The presence of such large interstellar objects hints that planetary systems, capable of forming substantial comet populations, may be common throughout the galaxy. Moreover, the size affects how cosmic radiation influences the object during its interstellar journey. Larger objects retain more of their original composition in their interiors, shielded from the effects of cosmic rays that gradually alter surface materials over millions of years. This preservation means that spectroscopic studies of this comet could reveal relatively uncontaminated samples of materials from its birth environment. The dramatic size difference between our two interstellar visitors also raises intriguing questions about selection effects in our observations. Are we seeing a representative sample of interstellar objects, or just the tip of a cosmic iceberg? When Atlas first detected this interstellar comet, it was traveling at 137,000 miles per hour, relative to our solar system. That velocity represents 38 miles every single second, fast enough to cross the entire United States in less than 2.5 minutes. To understand this cosmic speed, imagine standing beside a highway where cars travel at 70 miles per hour. This interstellar visitor would flash past nearly 2,000 times faster than highway traffic, covering the distance from New York to Los Angeles in the time it takes to brew a cup of coffee. But speed in space behaves differently than speed on Earth. As the comet falls deeper into our sun's gravitational well, it accelerates dramatically. Just as a marble speeds up when rolling downhill, this cosmic wanderer gains velocity as it approaches the sun. By the time it reaches its closest approach in October, the comet will be racing at over 160,000 miles per hour. This acceleration demonstrates the immense gravitational power of our star. The sun's gravity reaches across billions of miles of space, gently tugging on this interstellar visitor and bending its path from a straight line into a graceful hyperbolic curve. The comet arrived from interstellar space in a nearly straight trajectory, but the sun's influence gradually curves its path until it swings around our star like a cosmic slingshot. The extreme velocity creates challenges that astronomers rarely face when studying normal solar system objects. Most comets and asteroids move relatively slowly across the sky, allowing telescopes to track them for hours or days with the same instrument settings. This interstellar speedster races across telescope fields of view so quickly that observers must constantly adjust their pointing and tracking to keep it centered. Professional telescopes designed to follow the slow, predictable motions of stars struggle to keep pace with this cosmic sprinter. The object moves fast enough that exposure times must be carefully calculated to prevent the comet from creating streaks across the detector during long observations. Astronomers must balance the need for long exposures to gather faint light against the motion that would blur their images. The high velocity also compresses the observation window dramatically. Unlike periodic comets that return every few years or decades, providing multiple opportunities for study, this visitor will pass through our solar system exactly once. When it departs, it will carry its secrets back into the depths of interstellar space, never to return to our vicinity. The speed differential between our solar system and this interstellar wanderer reveals something profound about galactic motion. Our entire solar system orbits the center of the Milky Way galaxy at about 500,000 miles per hour. But this comet arrived from a different part of the galaxy with its own orbital velocity. The collision of these two cosmic reference frames creates the relative motion that makes interstellar objects so distinctive. Understanding these velocities helps astronomers trace the object back to its possible origin and forward to its future destination. After its brief encounter with our Sun, this cosmic messenger will resume its journey into the vast darkness between stars. Every photon of light reflected from this interstellar comet carries information that has traveled across the galaxy for millions of years. When astronomers aim spectrographs at the comet's glowing coma, they are essentially performing chemistry experiments on materials that formed around a distant star. Each element and molecule absorbs and emits light at specific wavelengths, creating a unique fingerprint that reveals the composition of the gas and dust streaming away from the nucleus. These spectroscopic signatures are like cosmic DNA carrying the genetic code of another planetary system. The initial spectroscopic observations revealed both familiar and surprising elements in the comet's coma. Water vapor showed up immediately, confirming that H2O ice forms around other stars, just as it does in our solar system. Carbon monoxide and carbon dioxide appeared in the expected ratios, suggesting that the basic chemistry of comet formation operates similarly across different stellar environments. But subtle differences in the isotope ratios tell a more complex story. Isotopes are versions of the same element with different numbers of neutrons in their nuclei. The ratio of different oxygen isotopes, for example, depends on the specific conditions present when the comet formed billions of years ago. These ratios act like a cosmic birth certificate, revealing details about the temperature, pressure, and available materials in the original stellar nebula. The deuterium to hydrogen ratio in the water vapor provides particularly valuable information. Deuterium is heavy hydrogen, containing one proton and one neutron instead of just a proton. The amount of deuterium incorporated into water ice depends on the temperature and density conditions during formation. By measuring this ratio, astronomers can estimate whether the comet formed in the warm inner regions of its original planetary system or in the cold outer reaches where most comets are born. Early measurements suggest that this interstellar visitor formed in conditions similar to those found in the outer regions of our own solar system. The chemical signatures match most closely with comets from our Kuiper belt, the reservoir of icy bodies beyond Neptune. This similarity suggests that the basic processes of planetary system formation may be remarkably consistent across different stars. However, some trace elements show intriguing differences from solar system norms. The relative abundance of certain metals in the coma, dust particles, hints at a parent star with a slightly different composition than our Sun. Stars that formed from gas clouds enriched by previous generations of stellar explosions can have higher concentrations of heavy elements, and these differences get incorporated into the planets and comets that form around them. The organic compounds detected in the coma present the most tantalizing possibilities. Simple, carbon-based molecules like formaldehyde and methanol are common in comets throughout our solar system, but this interstellar visitor may carry more complex organic chemistry. Advanced spectroscopic techniques can identify molecular structures that reveal the chemical evolution that occurred in its birth environment. These chemical signatures provide our first direct samples of materials from another planetary system, offering insights that would otherwise require interstellar travel to obtain. But the tale of this cosmic visitor tells an even more detailed story about conditions in its distant home. The graceful tail streaming from this interstellar comet is more than just a beautiful celestial display. It is a time machine carrying information from another star system. As solar wind pushes gas and dust away from the comet's nucleus, it creates two distinct types of tails that reveal different aspects of the object's composition and history. The ion tail, made of electrically charged gas molecules, points directly away from the sun like a cosmic windsock. The dust tail follows a slightly curved path, shaped by the balance between solar radiation pressure and the comet's orbital motion. The ion tail provides a real-time chemical analysis of the gases being released from the nucleus. As ultraviolet radiation from the sun strips electrons from gas molecules, it creates glowing ions that emit light at characteristic wavelengths. Sodium ions glow yellow, carbon monoxide ions appear blue, and water ions shine with a distinctive blue-green hue. This natural spectroscopy reveals not just what elements are present, but their relative abundances. The dust tail tells a different story about the solid materials incorporated into the comet when it formed. Microscopic analysis of the light scattered by dust particles reveals their size distribution, composition, and structure. Unlike gas molecules that can be altered by chemical reactions during the comet's journey through space, dust grains preserve a more direct record of conditions in the original stellar nebula. The ratio between gas and dust production rates indicates how the comet formed and evolved in its birth environment. Comets that formed closer to their parent star tend to have lower ice content and produce less gas relative to dust. Those that formed in the cold outer regions of planetary systems are typically more ice-rich and generate spectacular gas tails when they approach a star. Preliminary observations suggest this interstellar comet has a gas-to-dust ratio similar to long-period comets from our own solar system's Oort cloud. This similarity implies that the visitor formed in the cold outer reaches of its original planetary system, where temperatures were low enough for volatile ices to condense and accumulate on solid grains. The tail also reveals information about the magnetic environment around the comet's parent star. Different stellar magnetic field strengths during planetary system formation can influence how dust grains clump together and grow into larger bodies. The size distribution of dust particles in the tail carries signatures of these ancient magnetic processes. As the comet continues its approach toward the sun, the tail will grow longer and more spectacular. The increased solar heating will sublimate ice from deeper layers of the nucleus, potentially revealing materials that have been frozen since the comet's formation billions of years ago. These pristine materials could contain organic molecules or mineral structures that provide direct evidence of the chemical conditions in another stellar system. The tail's evolution over time also constrains models of how the comet has changed during its millions of years in interstellar space. Cosmic radiation gradually alters surface materials, but the interior remains largely unaffected. As the sun's heat penetrates deeper into the nucleus, astronomers can essentially peel back layers of time, studying materials that represent different epochs in the comet's history. The ability to study an active interstellar comet represents an unprecedented opportunity in planetary science. Never before have we been able to track these dynamic processes in real time for an object that originated around another star. Following an interstellar comet across the sky requires telescope technology pushed to its absolute limits. The fastest military sniper bullets travel at about 3,000 feet per second. This interstellar comet moves at 200,000 feet per second, making it roughly 67 times faster than a speeding bullet. But unlike a bullet that travels in a straight line for seconds, this cosmic projectile follows a curved path across the sky for months, requiring constant adjustments to keep it in view. Modern telescopes use sophisticated computer-controlled systems to track moving objects. The telescope mount calculates the object's predicted position thousands of times per second, making tiny adjustments to counteract Earth's rotation and the target's motion through space. For most asteroids and comets, this tracking is routine. For interstellar objects, it pushes these systems to their engineering limits. The challenge begins with determining exactly where the comet will be from one night to the next. Normal solar system objects follow predictable elliptical orbits that astronomers can calculate years in advance. Interstellar objects follow hyperbolic trajectories that are more difficult to predict, especially when outgassing from the nucleus creates small but measurable changes in the orbit. Professional observatories around the world coordinate their observations to maximize coverage as the comet races across different parts of the sky. When the object sets below the horizon at one observatory, telescopes on the other side of the Earth take over the watch. This global relay ensures continuous monitoring, despite the Earth's rotation and the comet's rapid motion. Advanced imaging techniques help extract maximum information from each observation, rather than taking single long exposures that would streak as the comet moves. Astronomers capture series of shorter images that can be combined mathematically to enhance faint details. This technique, called shift and stack processing, allows the comet to remain sharp while background stars blur into streaks. The most sophisticated observatories can track moving objects so precisely that they can maintain focus on targets traveling at interstellar speeds for hours at a time. The Hubble Space Telescope, orbiting above atmospheric distortion, achieved some of the sharpest images ever obtained of an interstellar object by using this advanced tracking capability. Radio telescopes face even greater challenges when attempting to study interstellar visitors. Radio observations require extremely precise pointing accuracy, often measured in fractions of an arc-second. The combination of the object's motion and the Earth's rotation means that radio telescopes must constantly adjust their pointing while maintaining the precise frequency tuning needed to detect faint signals. The Doppler effect adds another layer of complexity to radio observations. As the comet moves toward or away from Earth at tens of miles per second, it shifts the frequency of any radio signals by amounts that can overwhelm the narrow frequency ranges used by sensitive radio receivers. Astronomers must continuously adjust their receiver frequencies to compensate for this cosmic Doppler shift. Despite these challenges, the global astronomy community has developed unprecedented coordination in tracking this interstellar visitor. Observations from ground-based telescopes, space-based observatories, and even amateur astronomers contribute to a comprehensive picture of the comet's behavior and composition. This coordinated effort will reach its climax as the comet approaches its closest point to the Sun in late October. October 30th, 2025 will mark the most dramatic moment in this interstellar comet's billion-year journey. On that date, the cosmic wanderer will reach perihelion, its closest approach to our Sun, at a distance of 130 million miles. This places it just inside the orbit of Mars, close enough for the Sun's intense radiation to drive spectacular activity from the comet's nucleus. For comparison, this is about 40% closer to the Sun than Earth's average distance, subjecting the comet to solar heating nearly 3 times more intense than what our planet receives. The approach to perihelion will transform this already active comet into a cosmic spectacular. As the Sun's heat penetrates deeper into the nucleus, it will sublimate ice that has remained frozen since the comet's formation around another star billions of years ago. This fresh ice, protected by outer layers during the long interstellar journey, may contain pristine materials that reveal the original chemistry of the comet's birth environment. The increased activity will make the comet's tail grow dramatically longer and brighter. Models predict that the tail could extend for millions of miles, potentially making it visible to amateur astronomers with modest telescopes despite the comet's enormous distance from Earth. The spectacle will offer a rare opportunity for citizen scientists to contribute observations of an object that originated in another star system. However, the intense solar heating also creates observational challenges. As the comet approaches perihelion, it moves closer to the Sun's position in Earth's sky, making it increasingly difficult to observe from the ground. The bright solar glare will eventually overwhelm the comet's light, forcing astronomers to suspend observations until the object emerges on the far side of the Sun in early December. This solar conjunction represents a critical gap in the observational coverage, occurring precisely when the comet is most active. Space-based observatories like the Solar and Heliospheric Observatory, designed to study the Sun's corona, may be able to capture images of the comet during this close passage. These specialized instruments can block the Sun's disk while observing the surrounding space where the comet will be traveling. The gravitational effects of the Sun's proximity will also bend the comet's trajectory most dramatically during perihelion passage. The hyperbolic orbit that brought this visitor from interstellar space will be modified by the Sun's gravity, potentially changing the comet's future path through the galaxy. Precise measurements of the comet's position during this phase will help astronomers predict its destination after leaving our solar system. The extreme solar heating may also reveal structural information about the comet's nucleus. If the nucleus contains significant amounts of more volatile ices like carbon monoxide or nitrogen, they will sublimate explosively near perihelion, potentially fragmenting the nucleus or creating dramatic outbursts of activity. Such events would provide unique insights into the internal structure and composition of this interstellar visitor. For planetary scientists, perihelion passage represents the peak opportunity to study how materials from another star system respond to our Sun's radiation. The comparison between this comet's behavior and that of native solar system comets could reveal fundamental differences in composition or structure that reflect different formation environments. As perihelion approaches, telescopes around the world will maintain continuous surveillance of this cosmic visitor. The observations gathered during these crucial weeks will provide the most detailed portrait ever obtained of an active interstellar object. Unlike the predictable comets that grace our skies every few years or decades, this interstellar visitor is making a once-in-forever appearance. The difference lies in the fundamental nature of its orbit. Most comets in our solar system follow elliptical paths that bring them back to the inner solar system repeatedly. Halley's Comet returns every 76 years. Comet Hale-Bopp visits roughly every 2,500 years. These periodic comets are gravitationally bound to our Sun, trapped in endless loops that have continued for millions of years. This interstellar comet follows a hyperbolic trajectory, a mathematical curve that approaches the Sun once and then diverges into infinity. Picture throwing a ball at a wall. An elliptical orbit is like a ball attached to a rubber band that stretches and contracts but always returns. A hyperbolic orbit is like a ball thrown so hard that it bounces off the wall and flies away forever, never to return. The comet's excessive speed provides the key to understanding its trajectory. At 137,000 miles per hour, it carries far more kinetic energy than the Sun's gravity can capture permanently. Our star can bend the comet's path and accelerate it during its passage, but it cannot slow the visitor enough to trap it in a closed orbit. The comet will swing around the Sun like a cosmic slingshot and head back into the depths of interstellar space. After perihelion passage, the comet will begin its eternal journey away from our solar system. It will first cross Mars's orbit in November, then Jupiter's orbit in early 2026. By 2028, it will pass beyond Saturn, entering the outer reaches of our solar system, where sunlight becomes too faint to drive significant cometary activity. The comet will continue outward for thousands of years, gradually fading as it moves farther from the Sun's warming influence. Eventually, it will cross the heliopause, the boundary where the solar wind gives way to the interstellar medium. At that point, roughly 100 years from now, it will officially return to interstellar space, carrying with it subtle changes caused by its brief encounter with our Sun. During its passage through our solar system, the comet will lose a small fraction of its mass through sublimation. This material will remain behind, adding microscopic amounts of interstellar dust and gas to our solar system's inventory. In a sense, our Sun will have permanently captured a tiny sample of matter from another star system, even as the main body of the comet escapes back to the galaxy. The gravitational interaction with our Sun will also slightly modify the comet's future trajectory through the galaxy. While the change is small, it means the comet will follow a different path than it would have without this solar encounter. In millions of years, this tiny deflection could determine which star system the comet visits next, if any. The one-way nature of this encounter makes every observation precious. Unlike periodic comets that offer multiple opportunities for study over centuries or millennia, astronomers have only one chance to learn everything possible about this interstellar messenger. Once it departs, human civilization will likely never see this particular object again, making current observations a unique window into another stellar system. The Atlas telescopes perceive a universe invisible to human vision, detecting cosmic wanderers too faint for any earthbound observer to notice. Human eyes can see stars down to about 6th magnitude under perfect dark sky conditions. This represents the sensitivity limit evolved over millions of years for spotting predators and prey on the African savanna, not for hunting cosmic visitors traveling between star systems. The Atlas cameras reach magnitude 20, detecting objects 100,000 times fainter than the dimmest stars visible to the naked eye. To understand this sensitivity difference, imagine trying to spot a match flame. With your naked eyes, you might see it from across a football field on a clear night. The Atlas system could detect that same match flame from over 3,000 miles away, roughly the distance from New York to Los Angeles. This extraordinary sensitivity comes from combining large digital sensors with precise optics and sophisticated computer processing. Each Atlas telescope captures light for 30 seconds in every exposure, accumulating photons from faint objects that would be completely invisible in shorter glimpses. The human eye integrates light for only about 1/30th of a second before resetting, making it impossible to build up enough signal to see these dim cosmic visitors. The electronic detectors can store light indefinitely, building up images of objects millions of times too faint for biological vision. The wavelength sensitivity of Atlas extends beyond human perception into the near-infrared. While our eyes detect light from blue through red, the Atlas cameras respond to wavelengths that extend into the heat radiation emitted by warm objects. This infrared sensitivity allows the system to detect asteroids and comets by their thermal emission, even when they reflect very little sunlight. Computer processing amplifies these capabilities even further. The Atlas software automatically compares each new image against reference catalogs containing positions of millions of known stars and galaxies. Any object that appears in a new position gets flagged for further analysis. This automated comparison happens within minutes of each exposure, identifying moving objects in real time as they travel across the sky. The system's temporal resolution provides another advantage over human perception. By taking 4 images of each sky region, separated by 10-minute intervals, Atlas can detect motion that would be imperceptible to human observers. An asteroid moving at typical speeds covers only a few arc-seconds in 10 minutes, an angular distance smaller than the apparent size of a grain of sand viewed from 100 feet away. Atlas also perceives the sky in wavelengths selected specifically for asteroid detection. The system uses filters that enhance the contrast between asteroids and the background sky, making faint objects more detectable than they would be in natural sunlight. These specialized filters remove much of the atmospheric glow that limits ground-based observations, effectively giving the telescopes cleaner views of space. The global network effect multiplies these individual capabilities. While a human observer can only see one hemisphere of the sky at a time, the 4 Atlas stations together monitor the entire dark sky every 24 hours. This continuous coverage ensures that no potentially threatening object can approach from any direction without detection. Perhaps most importantly, Atlas never sleeps, never gets tired, and never loses concentration. The robotic sentinels maintain their vigil every clear night, scanning the cosmos with inhuman persistence for the next visitor from the stars. The 4 Atlas telescopes, separated by thousands of miles, operate as a single coordinated organism, with each station contributing to a collective intelligence greater than the sum of its parts. When the Chilean telescope detects a moving object, computers at all 4 sites immediately receive the discovery data. Within minutes, the other telescopes can point toward the same region of sky to gather confirming observations. This rapid cross-verification eliminates false alarms caused by cosmic rays, satellite trails, or instrumental artifacts that might fool a single telescope. The global distribution creates overlapping fields of view that provide multiple perspectives on the same cosmic events. When an object appears near the horizon for one telescope, it may be perfectly positioned for detailed observations by another station thousands of miles away. This geographic diversity ensures that atmospheric conditions, local weather, or technical problems at one site do not interrupt the continuous monitoring of important discoveries. Each telescope contributes its unique observational advantages to the collective effort. The Hawaiian stations benefit from exceptional atmospheric stability above the Pacific Ocean, providing the steadiest images for precise position measurements. The South African telescope operates in the world's driest climate, minimizing atmospheric absorption that can dim faint objects. The Chilean site sits at high altitude in the Atacama Desert, where crystal-clear skies allow detection of the faintest possible targets. The time zone separation provides perhaps the most crucial advantage of the global network. As Earth's rotation carries one telescope into daylight, others are entering their optimal observing hours. A threatening asteroid discovered by the morning twilight at one site can be immediately tracked by telescopes entering their evening observing sessions on the other side of the world. This 24-hour coverage eliminates the gaps that plagued earlier survey systems. Data processing occurs simultaneously at all sites, with sophisticated algorithms comparing observations across the network in real time. If one telescope detects an object moving at high angular velocity, the system automatically alerts other telescopes to search for the same target in their current or upcoming observations. This coordinated response dramatically improves the chances of tracking fast-moving objects that might otherwise be lost. The network architecture also provides crucial redundancy for protecting Earth from asteroid impacts. If a large asteroid were discovered on a collision course with Earth, the loss of any single telescope due to weather, equipment failure, or other problems would not interrupt the tracking needed for impact prediction. The remaining telescopes could maintain sufficient observations to refine the object's orbit and predict impact location and timing. Communication between sites happens through dedicated high-speed internet connections that ensure observation data reaches all telescopes within seconds of capture. Advanced compression algorithms minimize the bandwidth required to share the enormous data volumes generated each night, allowing real-time coordination despite the vast distances between stations. The collective intelligence of the Atlas network extends beyond simple detection to sophisticated orbit determination. By combining observations from multiple sites, taken at slightly different times and viewing angles, the system can calculate preliminary orbits for new discoveries within hours instead of the days or weeks required by single telescope surveys. This networked approach has revolutionized humanity's ability to monitor threats from space and discover visitors from other star systems. The coordinated global surveillance represents our species' most advanced early warning system for cosmic hazards. Every clear night, a coordinated network of robotic guardians scans the cosmos for objects that could threaten human civilization. Atlas represents just one component of humanity's growing planetary defense infrastructure. The system works alongside NASA's Catalina Sky Survey in Arizona, the Linear Project in New Mexico, and the NEOWISE Space Telescope to create overlapping coverage that ensures no significant threat can approach undetected. Together, these surveys have catalogued over 90% of near-Earth asteroids larger than 1 kilometer across, essentially eliminating the risk of a surprise civilization-ending impact. The warning times provided by this global network scale with object size in ways that match our defensive capabilities. A 2-mile-wide asteroid, capable of causing a global catastrophe, would be detected decades before impact, providing ample time to develop and deploy deflection missions. A 300-foot asteroid, large enough to devastate a metropolitan area, receives several weeks of warning. Even 60-foot objects that could damage cities get spotted days in advance. These warning times align with humanity's emerging asteroid deflection technologies. NASA's DART mission successfully demonstrated that spacecraft impacts can alter asteroid trajectories, proving that we possess the basic technology needed to defend Earth from cosmic threats. The European Space Agency's Hera mission will provide detailed follow-up observations of the DART impact, refining our understanding of how to deflect dangerous asteroids most effectively. The detection network also supports rapid response protocols that could save millions of lives even when deflection is not possible. For small asteroids that might impact populated areas, precise tracking allows authorities to predict impact locations within a few miles. This accuracy enables targeted evacuations of the most dangerous zones while avoiding unnecessary panic in surrounding regions. Atlas contributes crucial capabilities to this defensive network through its specialized focus on last-minute detections. While other surveys excel at finding large objects years in advance, Atlas fills the critical gap for smaller threats that might appear suddenly. The system's ability to scan the entire sky every night ensures that even objects approaching from previously unmonitored directions cannot achieve complete surprise. The global coordination extends beyond just telescopes to include sophisticated orbit calculation centers that process discovery data in real time. The Minor Planet Center at the Smithsonian Astrophysical Observatory serves as the international clearinghouse for asteroid discoveries, collecting observations from surveys worldwide and calculating precise orbits within hours of detection. NASA's Planetary Defense Coordination Office maintains continuous liaison with international space agencies, military organizations, and emergency management authorities to ensure that asteroid threat information reaches decision-makers immediately. Automated alert systems can notify key personnel within minutes of detecting a potentially hazardous object, triggering coordinated response protocols that span multiple nations and organizations. The detection capabilities continue to improve each year as new telescopes join the global network and existing systems receive upgrades. The upcoming Vera Rubin Observatory will revolutionize the field by detecting asteroids hundreds of times fainter than current surveys can reach. This next-generation facility will discover an estimated 5 million new asteroids during its first decade of operation. Space-based observatories, like the planned NEO Surveyor mission, will extend surveillance into wavelengths and sky regions inaccessible from the ground. These orbital sentinels will provide the final pieces needed for comprehensive protection of our planet from cosmic threats. The era of interstellar object discoveries has only just begun, with revolutionary surveys about to transform our understanding of visitors from other star systems. Theoretical models predict that between 1 and 10,000 interstellar objects pass through our solar system at any given time. Most of these cosmic wanderers remain in the cold outer reaches, beyond Neptune, too distant and faint for current telescopes to detect. But as our survey capabilities improve, we will begin finding these elusive visitors in unprecedented numbers. The Vera Rubin Observatory, beginning operations in Chile, will revolutionize interstellar object detection with its unprecedented combination of sensitivity and field of view. This next-generation facility can image the entire visible sky every 3 nights, reaching objects hundreds of times fainter than current surveys. Computer models suggest that Rubin will discover between 1 and 3 interstellar objects every year, building a statistical sample that will transform our understanding of these cosmic messengers. Each new discovery will add pieces to a cosmic puzzle that spans the entire galaxy. Some interstellar objects will arrive from the direction of nearby star systems, potentially allowing astronomers to trace them back to their origins. Others will carry chemical signatures that reveal the composition of stellar environments hundreds of light years away. The accumulated data will create the first comprehensive map of material exchange between star systems. Future surveys will also detect much smaller interstellar objects than current capabilities allow. While the first few discoveries involved objects hundreds of feet to miles across, improved telescopes will find visitors as small as cars or houses. These tiny fragments may represent chips knocked off larger bodies by cosmic collisions, carrying samples of planetary surfaces or asteroid cores from distant worlds. The James Webb Space Telescope and upcoming extremely large telescopes will provide unprecedented spectroscopic capabilities for studying interstellar visitors in detail. These advanced instruments will detect trace organic compounds and exotic ices that reveal the chemical evolution occurring in other stellar environments. Such studies could even identify biosignatures, chemical indicators of life, preserved in interstellar objects from biologically active worlds. Specialized missions designed to intercept and study interstellar objects are already in development. The European Space Agency's Comet Interceptor mission will station a spacecraft at the L2 Lagrange point, ready to deploy probes toward any suitable interstellar visitor. Such missions could analyze surface materials directly, providing detailed chemical and isotopic information impossible to obtain from ground-based observations. Advanced computational models will help predict when and where new interstellar objects might appear. By understanding the galactic dynamics that eject objects from planetary systems, astronomers may be able to forecast arrival times and trajectories for objects from specific stellar regions. This predictive capability could enable targeted observations that capture interstellar visitors earlier in their approach to our Sun. The discovery rate will accelerate dramatically as space-based observatories join the search. Free from atmospheric interference and able to observe continuously, orbital telescopes will detect interstellar objects across the entire electromagnetic spectrum. Infrared surveys will find dark objects invisible to optical telescopes, while ultraviolet observations will study gas emissions from active comets. Artificial intelligence and machine learning algorithms will automate much of the discovery and classification process, enabling surveys to process vastly larger datasets than human astronomers could handle manually. These technological advances will usher in an era where interstellar object discoveries become routine rather than extraordinary events. The discovery of visitors from other star systems has fundamentally altered humanity's understanding of our place in the galaxy and the processes that govern planetary system evolution. Before the first interstellar object arrived in 2017, our knowledge of planetary systems beyond our own came entirely from indirect observations. Exoplanet discoveries revealed the existence of thousands of worlds orbiting distant stars, but we could only infer their properties from the tiny amounts of starlight they blocked or reflected. Interstellar objects provide our first direct samples of materials from these alien worlds. The chemical analysis of interstellar visitors reveals that the basic processes of planetary formation operate similarly across different stellar environments. The water, carbon dioxide, and other compounds found in interstellar comets match those seen in our own solar system, suggesting that the laws of physics and chemistry produce remarkably consistent results, regardless of stellar type or galactic location. However, subtle differences in isotope ratios and trace element abundances hint at the enormous diversity that exists among planetary systems. Some interstellar objects carry signatures of formation around stars richer in heavy elements than our Sun, while others suggest origin in metal-poor environments typical of the galaxy's outer regions. These variations provide crucial constraints for models of how different stellar compositions affect planet and comet formation. The discovery of interstellar objects also reveals the dynamic nature of planetary systems throughout the galaxy. Every star system apparently ejects some fraction of its asteroids and comets into interstellar space through gravitational interactions with giant planets. This process of cosmic cross-contamination means that material formed around one star can eventually be incorporated into other planetary systems, potentially spreading the chemical ingredients for life across vast galactic distances. The size distribution and arrival rates of interstellar objects constrain models of planetary system architecture throughout the galaxy. The fact that we have detected several kilometer-sized interstellar visitors suggests that large comet reservoirs, like our Oort cloud, are common features of mature planetary systems. The absence of planet-sized interstellar objects implies that gravitational ejection mechanisms primarily affect smaller bodies. Statistical analysis of interstellar object trajectories provides insights into the structure and dynamics of our local galactic neighborhood. The directions from which these visitors arrive reflect the orbital motions of nearby star systems and the gravitational influences of massive stellar structures. Future discoveries may reveal patterns that map the large-scale organization of matter in our region of the galaxy. The study of interstellar objects has also highlighted gaps in our understanding of small body evolution over cosmic timescales. The mysterious acceleration of the first visitor challenged conventional models of how objects behave during million-year journeys through interstellar space. These discoveries force scientists to consider new physical processes and chemical reactions that operate only during the extreme conditions of interstellar travel. Perhaps most profoundly, interstellar objects demonstrate that our solar system exists within a dynamic galactic ecosystem where material constantly flows between star systems. The traditional view of planetary systems as isolated islands in space has given way to recognition that they are interconnected nodes in a vast network of chemical and physical exchange. This new perspective suggests that life, if it exists elsewhere in the galaxy, may have mechanisms for spreading between star systems. Interstellar objects could serve as vehicles for transporting organic compounds or even dormant microorganisms across the vast distances between stars. The journey from the mysterious first interstellar visitor to today's sophisticated detection networks has revealed profound truths about our cosmic neighborhood and humanity's place within it. The enigmatic, needle-shaped wanderer of 2017 taught us that the universe contains objects unlike anything in our experience. Its bizarre acceleration without visible outgassing challenged our understanding of small body physics and demonstrated that even our most fundamental assumptions about space rocks could be wrong. The hydrogen gas theory that eventually explained its behavior showed how cosmic radiation can transform ordinary ice into invisible rocket fuel during million-year journeys between stars. More importantly, that first visitor revealed how unprepared we were to study such remarkable discoveries. The object was already departing our solar system when astronomers found it, providing only a brief window for observations before it disappeared forever into interstellar space. This cosmic near-miss catalyzed the development of comprehensive sky surveys designed to spot future visitors much earlier in their approach. The Atlas network represents humanity's response to that wake-up call. By scanning the entire sky every clear night, these robotic sentinels ensure that no future interstellar visitor will catch us unprepared. The system that detected the third interstellar object in July 2025 exemplifies how coordinated global surveillance can transform astronomical discovery from lucky accident into systematic exploration. The active comet discovered by Atlas provides a perfect counterpoint to the first mysterious visitor. Here is an object that behaves exactly as astronomers expect, following well-understood physics while carrying chemical signatures from another star system. Its spectacular tail and coma offer unprecedented opportunities to study materials that formed around a distant star billions of years ago. Together, these discoveries demonstrate that interstellar objects come in varieties we are only beginning to understand. Some may be exotic wanderers, unlike anything in our solar system, while others prove that the same physical processes operate throughout the galaxy. Both types provide invaluable information about planetary system formation and evolution on cosmic scales. The technological advances driven by interstellar object research benefit all of astronomy and planetary defense. The same networks that hunt for cosmic visitors also protect Earth from asteroid impacts, discover supernovae in distant galaxies, and track satellites that threaten space missions. The computational techniques developed to analyze faint moving objects have applications from medical imaging to autonomous vehicles. Perhaps most significantly, these cosmic messengers have changed how we think about our solar system's place in the galaxy. We now understand that vast amounts of material flow between star systems, creating an interconnected web of chemical exchange that spans the entire galaxy. Our Sun participates in this cosmic recycling program, both receiving visitors from other stars and contributing its own asteroids and comets to the interstellar population. The story that began with one strange visitor racing through our solar system has evolved into a new chapter of astronomical discovery. Advanced surveys will soon detect interstellar objects routinely, building a comprehensive catalogue of materials ejected from planetary systems throughout our galactic neighborhood. We stand at the threshold of an era where visitors from other star systems will reveal the chemical and physical diversity of worlds we may never visit directly, bringing the cosmos to us, one cosmic wanderer at a time.